Okay, and we're back, and this one, we want to do something with identifying the basics of binary orbits. So a binary system, probably the best example to think in terms of would be the Earth-Moon system. And so often most people think that the Moon is an orbit around the Earth, which is true, but what a lot of people don't realize is that the Earth is actually orbiting the Moon as well. So we have these two objects in motion around each other, which leads to some pretty interesting effects. We just want to understand the very basics of these. So we have this binary orbit, a binary system, and the really key ideas of how we're going to set this up include gravity, of course. Neither the Earth nor the Moon would stay in any kind of orbit if there wasn't any gravity. They'd fly off into space. So it's that neutral gravity we'll look at. We're going to assume circular orbits. So we'll use the basics of centripetal force to help us out. We're going to find out that the more massive object, in this case, say the Earth, is going to be in the smaller of the two circular orbits. The reason for this is it's the center of mass of the system that serves as the center of both orbits. And we'll draw a picture in about a minute so we can see what that looks like. Because gravity holds them, and gravity is serving as a centripetal force, the two objects have to be on opposite sides of their two orbits, and that'll show up in the picture. Now this also necessitates that the smaller object has to move faster. Both the objects, whether it's the Earth-Moon, the Earth-Sun, two stars going around each other, doesn't really matter what the system is. They have to have the same period. They take the same time to go once around their orbits. So here's kind of a little schematic of what this might look like. Just kind of generically, we're going to say that the mass on the left is 3 times bigger than the mass on the right. Okay, so let me erase this, and we'll just call this 3 times the mass. And each of these things will just have, use the symbol m for mass. They're a total distance away. And the first thing is, the center of mass of these two, imagine if you had this uneven dumbbell. Where could you balance the system? If we think of a line that connects the two, centers the two masses. Now the center of mass is going to be over here somewhere, closer to the bigger object. We can figure out exactly where it is using our definition for center of mass. Okay, it's the sum of each mass times its x position divided by the sum of the masses in the system, the total mass. Okay, so we're going to have 3m. I'm going to call this x equals 0 on the left-hand side. So we have the mass 3m times 0. Then we have this the smaller mass times its x position, which is going to be d. And that's divided by the total mass of the system. Okay, so in the end we end up, we have md divided by 4m, which is 1/4 the total distance. Okay, so that's how far away the center of mass is from the center of the big object. And that means that the smaller object is 3/4 of the way from the center of mass. These values are the two radii of the two orbits. Okay, so let me clean this up just a little bit here. I'm going to erase the center of mass calculation. And so if you're the little mass, the common center is that center of mass right here, dead, closer to the bigger object. So this little one is going to be at that radius around that common center of mass. Okay, so it goes in this big old circular orbit, centered on that position. And the big mass, its center, is also in orbit around that same common center of mass. Okay, so it's kind of like saying we have these two radii, radius 1, radius 2, for the two objects. Okay, I know that the picture gets messy in a hurry, but So what we're going to do with it should look somewhat familiar based on other stuff we know about gravity and satellites going around the Earth and things like that. Okay, so let's say, just for an example, we want to figure out how fast does the big object have to move. What's its orbital speed in this so-called binary system? Well, we're going to make use of centripetal force. It's a circular orbit, is our assumption. So 3m is its mass. Okay, and we're looking for its speed. Okay, and it's at some radius for the circle, for the orbit. Now you ask the question, well, what physically is the force that keeps you in that circle? Well, it's the gravity between the two objects. We're just going to use Newton's law of gravity. Now here's the thing that we have to be careful of. What distance do we use for Newton's law of gravity? Well, it's the total distance squared between the centers of the two objects. So we'll use big D squared. Okay, what's the radius of the large object? Well, the radius of the large object is 1/4 of the total distance between the two. So we have different distances in our two denominators. It's a little bit different than what some people might be used to doing for doing satellites going around the Earth. But anyhow, this simplifies a little bit. Oops, I forgot to spread of speed. We'll do that. So the mass of the big one drops out. One of the d's drops out. And if we solve for the speed of the large mass, we've got, what, big G. We've got the mass of the smaller object. This factor of 1/4 has to come up. So the 4 goes down in this denominator. And we have to square root both sides. Okay? So that's the orbital speed of the big mass. Now, if we happen to know the period, let's say we have a problem where the period is given. It's the same for both objects. So we could write this down in terms of distance divided by time. In a circular orbit, you have a constant speed. So the distance could be the circumference of the big one, the big object. So 2 pi times its radius, which is d/4, divided by the period. Okay, that's another way of writing down the same speed. These two things would be equivalent to each other. Okay, for the smaller object, let's just jot down what this would look like. Its mass times its orbital speed squared, I'll call it v2, over its circular radius, the orbital radius, okay, 3/4 of d. That's equal to the mutual gravity between the two. So the right-hand side is going to look exactly the same. Okay, we need the total distance between the objects. We just need plain old d squared over there. Okay. In a similar way, its mass drops out. One of the d's drops out. And when we solve for v2, we have gravity, the gravitational constant. We have the mass of the big one. This factor of 3/4 comes up. We have an additional factor of 3 on top, 4d on the bottom, and so we're looking at something like this for the speed of the smaller one. We could rewrite this as 2 pi times that orbital radius, 3/4 d for the small one, over exactly the same period. So we have a couple ways of writing each of these speeds. Okay, so that's all we're going to do for the time being. I just wanted to outline and remind ourselves what the key ideas are. Okay, let's go through that again. The same period for both objects. They're always on opposite sides as they spin around. That means that the bigger one is in the smaller orbit, and it's moving slower than the smaller object in your binary system. Okay. The common center of mass of the system is the center of both of those orbits. Okay, we're assuming circular orbits again. Okay, and it's gravity which is causing the centripetal force. That's how we set up these equations to figure out what these two objects are doing. Okay, so we'll leave it there, and until next time, we'll see you later.